And I think we can cover chapter 16 pretty effectively here, and then just introduce amino acids, and there are 6 of those that I want you to learn. That's your second recommendation, is to learn the 6 amino acids. That'll make it a lot easier next week. If you've got these learned, then the new information you hear next week will fall into place. So I'll just run through these slides and then I'll kind of know I covered everything. Just quickly, the physical properties, they're sweet, all right? They're sweet. They're, the degree of sweetness varies. Fructose is 73%. I don't know how they figured that out, but it's 73% sweeter than glucose. So grapes have a lot of fructose in them, and sometimes you get a grape and you think, wow, grapes are really sweet. Well, they may not actually have more sugar than something else, than a blueberry or something like that. They might have a little more sugar, but they also have a sugar that stimulates the taste buds more. They're solids at room temperature, like your table sugar in a sugar bowl. It's a white solid. You put it in water, it dissolves very readily, which is good because that's how it's transported in the circulatory system. Okay, let's look at them forming a ring. Now, in chapter, just very recently, just actually a few days ago, we looked at this situation where we said an alcohol can react with an aldehyde and form a hemiacetal. And what happens, this goes on the oxygen and this goes on the carbon, and you break this bond, you break that OH bond, and so what do you get? You get an OH here, and you get an OC bond there. And that's a hemiacetal. All right, this is why I emphasize this reaction in chapter 13, because I knew it was such a critical reaction with saccharides. So I'll take there's Danielle and Samantha's as an example here. We got an aldehyde right here. There's an aldehyde. And look at, we've got an alcohol. So this molecule has both of these functional groups on it. An aldehyde and an alcohol. Now this alcohol is too close. This alcohol right here, right down one carbon below it, is too close to do that. It looks pretty good, but it's just a little too close. That might be able to do it. That could do it. But it's carbon number 5. Why? I don't know. But this is what nature likes. It takes carbon number 5. The OH is on carbon number 5, and it adds across this carbon-oxygen double bond and forms a hemiacetal. Now, before I do this, let me just see what enantiomer we have here. Okay, this is on the right, so this is D-glucose. This OH here, down here, is on the right. Okay, so now watch what happens. 5 carbons away, right there. We're going to break this bond here, and we're going to put this oxygen on there. Or not, I'm sorry, this hydrogen. Hydrogen, I'll just take that one off. And we'll put this hydrogen on there. What happened? Oh yeah, and then I broke the bond in the wrong place. And so this was the double bond to that oxygen right there. It broke, we put the hydrogen there, and we're going to bind this to the oxygen. Six-membered ring. 5 carbons and an oxygen. All right, we've got a 6-membered ring. It's a heterocyclic ring now. It's got 5 carbons in it and an oxygen, and we have formed this hemiacetal. We got an OH, and we got a carbon-oxygen-carbon bond. This was the oxygen that was in the double bond. This is the oxygen that was the hydroxyl on carbon number 5. Is that right? No, this was the oxygen. Yeah, this was the oxygen in the carbon-oxygen double bond. Right. And that was the oxygen in the carbon-oxygen double bond. And there we go. Big deal. Wait, that's carbon number 6. This is carbon number 5. 1, 2, 3, 4, 5, 6. Carbon number 1 that had the aldehyde on it. 2, 3, 4, 5. And there's carbon number 6, a CH2OH group. Okay, now oh, that was right. What am I doing? They're actually right. Right? I'm making them wrong. Okay, now, so now the challenge is, how do we draw this thing? And how do we distinguish them from one another? And Haworth came in. Haworth, Haworth. Here you go. There's yours. Down, up, down, up. Yeah. Oh. That was a plastic bottle. Okay, so now we need to learn how to draw Haworth projections. And you can do that with your glucose. You should take a look at your glucose. Find carbon number 5. This is 1, 2, 3, 4, 5. And then try to cyclize it. Put your hydrogen on here and put your oxygen bound to there and cyclize yours. Now I'm going to take a look at it. Cyclize it. You should end up with a 6-membered ring with 5 carbons and an oxygen in it. Show them. Share with them.
Oh, yeah. There's supposed to be one. These are oh yeah.
Okay, when you're done, let me see it. You've got 5 carbons and an oxygen. Looks good. Now, I'm going to just switch a couple things around here. Put this one down here. And that one's up there. Put this one down here. We didn't pay attention. We only paid attention to that carbon one from the bottom in terms of where the OHs actually have to be. If we had paid closer attention to all of them, then they would have ended up like this, down, up, down. Why? You'll see what I mean by down and up, because we're going to take this and we're going to start looking at it like this, like that's flat. And then we're going to start asking our question, if this is flat, where is this? That's going to be very important. Is this above this thing or down here? There's going to be an alpha and a beta. There's going to be actually an alpha and a beta form of this. This is actually the beta form because this is up. And then this is going to be down, up, down, and this is up. This last carbon, number 6, is always up. And that's the Haworth projection. You see that. Okay, you got yours? Let's see. You got a 6-membered ring? You got a 6-membered ring here. This oxygen here should be in here. All right, so this is the oxygen that ends up here. But what are you doing here? I don't know how you did this, but this oxygen ends up here.
Adds to the alpha.
You want to back up a little bit? Try to find it. Just do this. I don't know how. So we had an album. Right. 1, 2, 3, 4, 5, 6. Here's 5. 5. And what's going to happen is this bond is great. This is going over there. There was the aldehyde. I'll leave the floppy bonds on there so you can see where they came from. Okay? You can see that this oxygen came from carbon number 5. This oxygen came from the aldehyde. Okay, so now, there we go. Now we got it.
So the double bond will become hydroxyl?
Yeah, the double bond becomes a hydroxyl.
And then the other one?
Becomes an ether. So the carbon that was on carbon number 5 is what forms that ether bond. All right, now that was a little bit important because now these would have been in the right position if I had told you what to do for carbon 4, 3, 2, exactly where to put things. We only worried about, for D-glucose, we only worried about carbon number 5 being like glyceraldehyde. So then we end up with, now here's the way we're going to look at this. I'm going to draw these on the board. Here's the molecule, but we're going to start looking at it with this 6-membered ring as kind of horizontal. Okay, we're going to look at that as horizontal. And then we're going to be asking the question, is this above or below the horizontal 6-membered ring? Is this above or this is below? That's above. This is below. That's above. This is below. So we have an OH below, an OH above, an OH below, and we have a CH2OH above. That's what we have for D-glucose. That's the way it's going to be. Below, above, below, above. And then we're going to look at this, and we're going to decide whether this is alpha or beta D-glucose. We're going to see. We're going to key in off of this. Where is this? Is it below the ring or above the ring? What? It's alpha. Yeah, this is below the ring. So this is alpha D-glucose. All right. You didn't do it. Here's carbon number 1, 2, 3, 4, 5. So actually, it's this bond breaks, and this goes on there. And then this bond goes on there. All right? This was an OH. This was a hydroxyl. And the O goes on the carbon, and the H goes on the oxygen. This was the carbon-oxygen double bond. So then now, if I flip this, I'm going to flip this over because I want this to be up. I flip this over, cut this down below the ring. This should be above the ring. This should be below the ring. This would have worked. I'm just getting those in the right positions. And this is above the ring. What we're going to do, I'm going to draw on the board. As I draw things, you're going to see this is horizontal. And we're going to be asking, where is this? It's below that horizontal plane. This is above it. This is below it. And this is above it. Okay? And we're going to learn how to draw those. All right, let me just look at this last one, and I'm going to show you how to draw these. Now, let's see, you still have a double bond right here. So let's see, is this your bottom carbon? There's your element. I see, there's your element. Did you take something off of it? Did you take an oxygen off of it? No, you took, oh, I see. See, you took a hydrogen off of it. That does not add. This adds. Here's where you get the hydrogen. You get the hydrogen off of the oxygen. Off of the hydroxyl.
17, 19, and
Yeah, so that doesn't add. That doesn't form a hemiacetal.
And the rest,
It's this. So let's see how this does. I'm going to break that bond right there. Tear that whole thing off. Hold on. Okay, put it on there. Try that off. There. You see how the hydrogen came off of this oxygen and went on that oxygen. Now take that bond and right there. Okay. Okay? Okay, now, the way we're going to look at this, we did it on the 6th carbon. Okay, sorry. Sorry. We did it 6th carbon. We did the bottom carbon. We did the next in the last. Take that nitrogen. Now, that. There we go. Now we got 5 carbons. 1, 2, 3, 4, 5, and then oxygen. See that we got 3 hydrogens. That's what it looks like. Don't worry about hydrogen too much. Now we do here 1, 2, 3, 4, 5 oxygen. Okay. Now, when I start drawing on the board, think about these 5 hydrogens and this oxygen in a plane, flat plane. And then we're going to be asking the question, is this thing above that plane? Is this above it or below it? Okay? This is below it, this is above it, this is below it, this is above it, and this is above it. No, this is the open chain. So we're done with this. This is the open chain version. Okay, now let me show you how to draw these. I'll make it simple. And on your sheet of paper, on a fairly big sheet of paper, draw a fairly large one of these. There's your oxygen. There's your 5 hydrogens, carbons, your 5 carbons. And then think of that as the bed of a trampoline, okay? Think of that like that. That's the bed of the trampoline, and the trampoline has legs on it. All right? There's your trampoline. But so imagine that you're looking at this, you're looking at this as a flat, you're taking that and looking at the flat bed of the trampoline, and sometimes you'll see them darken in the front edge, saying this is the front edge of your trampoline, and that's your back edge. And then there are 2 things on each one of these carbons. And the only thing I'm going to put on here are the OH groups for right now. The CH2OH group is going to be above the trampoline. We're going to have an OH below, an OH above, and an OH below. This is, so far here, we've got D-glucose. And we're going to put a qualifier out here to say where is the OH that's on carbon number 1. This would have been carbon number 1. This is carbon number 6. You should be able to see that here. This is carbon 6. This is carbon number 1. 2. These numbers aren't changing. This was carbon number 1 that had the aldehyde. That's where it ends up, right there. This is carbon number 5. So here's 2, 3, 4, here's 5, 6. That's what ends up in that chain there. So now we get into this position right here, and depending upon how that acetyl reaction, the orientation of that aldehyde, when that OH added across it, we can either get the OH below the ring or above the ring. Both of those forms exist. So if we get an OH down here, it is alpha D glucose. That is alpha D glucose. And beta D glucose is the other one. So you can take a look at yours and decide whether you have in front of you, and the way you got to look at it, you got to get this CH2OH back here. Here it is here. So I'm getting that above the ring. And then I have got my below, above, and this one, the OH is below, so this is alpha. This one has this OH right here, down below the ring. If I get the ring flat here, this is below the ring. This is alpha D glucose. Let me see. Anybody think they have beta? Yeah, here's beta. Okay, here's beta. This is above the ring, and the OH over here is above the ring. It's beta D glucose. Both of those exist. And at the other end of these stems here is a hydrogen. You don't have to draw it in there. It gets kind of too busy. So ignore the hydrogens. Just draw where are the OHs, where is the CH2OH. Always put the oxygen right here in that position, and always put the carbon number 6, the CH2OH, above in that position. That's a Haworth projection. You saw how particular we had to be with the Fisher projection, how we oriented everything. Well, now you also have to be particular about the way you look at the molecule. And then decide whether it is alpha or beta D-glucose. You should be able to draw both of these. Yeah.
Don't we have is it right? I'm looking at that.
Okay, don't look at it like that. Look at it like this. Turn that flat. Make this flat. This is up. See, this is down, up, down. Here's carbon number 1. Okay, so it doesn't do any good to look at it like this. You gotta get this flat. And then you look at this OH. Everything else is the same for alpha and beta D-glucose. They're all going to have a down, up, down, and this is going to be up. It's this position right here, and if this is down, what is it? Alpha. This one right here. This OH group. Yeah, we're not worried. We're asking ourselves, where is this OH group? It's below the ring. This is the ring. Here's the ring. It's flat, and this is below that ring.
Can you show us the order?
Beta would be right here. Switch those positions. That's beta. Everything else stays the same. Okay? So we're alpha and beta, the whole rest of the molecule, it's only carbon number 1. You look at the OH group on carbon number 1. And if it's above, it's beta. Below, it's alpha. Okay. Good. All right, so let's move on. The cyclization. There's a couple slides here just showing it again. You're just seeing it again. Here's the alpha, the OH is below. Here's the beta, the OH is above. Everything else is the same on the molecule. You can see the O is always up in this upper right-hand corner of the ring when you want to make this determination. Here it is with the front edge of it darkened. So you're kind of looking at it, you're saying, okay, I'm going to flip this up horizontal, so I'm looking straight on at it. Here's one where they're just the hydrogens. They're not even putting the lines on there. They just got OH below, above, below the CH2OH, and here's alpha, and here's beta. All right, so you can come back and examine these slides. Fructose will do the same thing, except it forms a 5-membered ring. Why does it do that? Because the carbonyl is not on carbon number 1, it's on carbon number 2. So there's 1, 2, 3, 4 carbons and an oxygen in a 5-membered ring. So this is a furanose ring, 5-membered with an oxygen. And for fructose, you get a CH2OH over here, and you get a CH2OH over here. If it is above the ring, it's alpha D fructose. If that's below, it's beta D fructose. The one that I will expect you to be able to draw alpha and beta of is D glucose. All right? Just kind of know that fructose also cyclizes, forms a little bit, it forms a smaller ring. So here's the pyran ring, pyranose ring you would get from glucose, 1, 2, 3, 4, 5 carbons and an oxygen. Here's the furan ring, 2, 3, 4 carbons and an oxygen. Well, we won't worry about that terminology. Oxidation, this is review from chapter 13, I guess it was, where we looked at the Benedict's reagent. Here's what happens in the body. Glucose can actually oxidize to gluconic acid, oxygen, and it's going to form the carboxylic acid and hydrogen peroxide. But then we use, then that gets into the Benedict's reagent, where you're doing that, but you're using copper to do the oxidation. And the blue copper turns red. Okay, phosphate esters. You can form a phosphate ester with the sugar. The CH2OH group can react with phosphoric acid, and you get a sugar phosphate. So glucose 6-phosphate. This is an important reaction, because what happens, glucose can kind of move across the cell membrane pretty easily, the glucose molecule. But when the glucose gets into a cell, the very first thing the cell does is attach a phosphate group to it, and it keeps it in the cell. Whenever the cell gets it, it's kind of like, I'm hungry, I just got some glucose, I don't want it going back out, I'm going to put a phosphate on it. It turns it into glucose 6-phosphate, and it stays inside the cell. So if the cell needs glucose for some energy, it's got it there. It won't migrate back out of the cell. Glucosamine. You may have heard of this. You can go to Walgreens, anywhere. GNC, buy that. You can buy glucosamine. People that have trouble with their knees or joints, they recommend taking glucosamine. And what is it? Okay, we've replaced that OH right there with an amine. That's glucosamine. There's N-acetyl beta-D glucosamine. All right, you got an acetyl group on this amine, like we would say an N-methyl group. That's an N-acetyl group on there. You don't have to memorize these molecules. The purpose of these is to show you that, yes, you have glucose and you do use it for energy, but your body will convert it into other things, to do other things with it. It's not just an energy source, it's also a nutrient of different sorts. All right, here, so far, every sugar we've seen, it's either had a carbonyl or a hydroxyl group on it. And remember, I told you on DNA, okay, Alejandra said RNA stands for ribonucleic acids. D in DNA stands for deoxyribo. What does that mean? It has lost that oxygen. This D stands, you got a deoxygenated ribose, sugar. It's lost one oxygen. So the sugar backbone in DNA is a unique sugar. There's not any other sugars that are deoxy sugars like that. So DNA contains this deoxyribo sugar. We'll see this in chapter 20. Chapter 20, you'll see what the sugar phosphate backbone looks like on RNA and DNA. All right, fructose. There's fructose. It's a ketose, and it cyclizes. This is kind of similar to a previous slide. So this is carbon number 1, 2, 3, 4, 5, 6. Or carbon number 1. Above is the alpha and below is the beta. Glucose, galactose. Did I give you the chapter 16 homework? I didn't do that. Okay. give it to you because I'm going to give you chapter 18 in a minute, so I'm not going to give you chapter 16. This is one of the questions. It just says basically draw these. Are you folks all brain dead? Yes. I can imagine. Studied for an exam. Now we're trying to do 2 more chapters. All right? So this is kind of like eating a big meal and then going away to digest it later. Right? So everybody got 16? So I'll tell you what, why don't you just go ahead and do number 9. Carefully draw the ring structures using Haworth projections of D-glucose and beta-D-glucose and beta-D-galactose. Then with a highlighter, highlight on each molecule the one key difference between them. What's the one key difference between glucose and galactose in the ring structure? I suggest you use pencil. You don't have to highlight it, you can circle it. Desiree, Crystal, Gail, and Hope. Well, you guys are to be commended for hanging around. We've lost a number of people here. What?
You mean just after?
Yeah, just after the exam.
Really?
Yeah, 3 or 4 people didn't come back after the exam. No, I don't know. They're not here. That's all. They're not here.
I told you.
No, when I said lost, I just mean they're not here right now. So they didn't hear any of that, okay? So what I will do, if you're in communication with any of these people, I am going to unlock these homework assignments so that you could print them off. That's for everybody's benefit. You start heading into the final and say, well, I'm going to just print one of these off and do it again. See if I can do it. See if I remember how to do that. You can always do that. I don't think they're all unlocked right now, but I'll try to remember to do that. Okay. All right. I'm going to speed through the rest of the slides on sugars and then just introduce amino acids so that I can get you the chapter 18 homework. These won't all be necessarily due on, well, I don't know. It might be due by the end of the day on Monday. Okay? Particularly since we want to try to have an exam on Tuesday. So let's do that. Okay, now you look at this. What we're comparing is beta-D glucose, beta-D galactose. So beta, that means here in carbon number 1 position, the OH is above the ring. Doesn't matter whether we're talking about beta glucose or beta galactose. Glucose, remember, the OH here is below, and then it's above, and then it's below, and the CH2OH is above. Beta-D galactose, the OH is below, this OH is above, and this OH is above. Everything else is the same except these two OHs are in different positions. That's a pretty subtle difference between glucose and galactose. But there are children born with the inability to digest galactose. They can digest glucose, but they lack the enzyme that will digest galactose with that subtle of a difference. You just flip this OH right up there. So if you think I'm paying unnecessarily a lot of attention to detail, I'm not. That's a subtle little thing. But a child can die from it because the galactose builds up as a toxin. Because they can't digest it, it becomes toxic to them. And there's ways of dealing with it. You just make sure they don't get any food that has galactose in it.
What kind of food galactose?
Well, milk has galactose in it. You just have to look at all the different foods that would have galactose in them and keep that out of the diet. Because they lack that enzyme. It's a genetic thing. They're born with it. When babies are born and they take a blood sample, and I know every state in the union, basically, they just keep adding tests to it every year. When our grandson was born 5 years ago, I think there was about 27 different things. They take a blood sample, they test for it. And they figure out, they do 27, whole different panel, 27 different genetic deficiencies that a child could be born with, and they identify them right away. Because if you identify them right away and avoid that ever being a problem for that individual, then it doesn't have an effect. But if that child goes for 6 months with galactosemia, it can start affecting the brain and different ways it affects the child, and they can be irreversible. Some of those effects can be irreversible. And so you have to catch these things right away and then figure out, okay, they need a special diet. This child needs a special diet. Can't eat ice cream. You know, can live, fine. You can live without ice cream.
What about the mom's milk? Would they be able to drink that?
Let me not say, because I'm not sure. We'll see here lactose in a minute, which is glucose and galactose. So lactose is a disaccharide that you'd find in milk. So yeah, mother's milk. All right, let's look at disaccharides. So you take here we go. Oh, this is maltose. What is maltose? You take alpha D-glucose and beta D-glucose and bind them together. You should be used to this now. An OH and an H forms water, and you get a carbon-oxygen-carbon bond. That's your glycosidic bond right there. I mean, that's just as if you had this going between the two rings. You got a carbon-oxygen-carbon bond, an ether linkage, and you're forming a disaccharide. There's two somethings in there. Is there two C's in disaccharide? Yeah, two C's. That's what I thought. Right here. You form a disaccharide. So maltose is alpha D-glucose and beta D-glucose, and you get maltose. There are three disaccharides that you should be familiar with, and what monosaccharides they're made up of. It's on the homework. Here is sucrose, table sugar. What is table sugar? A glucose and a fructose bound together. Carbon, oxygen, carbon bond. You got a disaccharide. And then lactose. Okay, this is the sugar that's in milk, Francesca. So lactose has a glucose and a galactose. So when children they're saying they're allergic to milk and they have to have soy milk or formula that's soy-based or something like that, they're getting away from lactose. Typically. Maybe for other reasons, but this would be one of them. Because they're allergic to it, and I'm not saying the only reason would be galactosemia, but galactosemia is the lack of being able to digest the galactose. All right, so those are the three disaccharides. Yeah, and you get these two different indications. Young, galactosemia. Older people, lactose intolerance. And usually what happens is an adult maybe gets away from drinking milk, doesn't eat any ice cream, goes for 4, 5, 6, 7 years like that, and they actually kind of lose the ability to digest that, and it causes abdominal kinds of problems, but it isn't life-threatening. Lactose intolerance isn't life-threatening. And I do think if you eat yogurts that have the culture in them and things like that, it can overcome that to some extent. Because now the probiotics in the yogurt can digest the lactose where the person themselves can't. So you can overcome lactose intolerance. Yeah, we just talked about this maltose. Okay, now polysaccharide. No, this is another disaccharide. Don't worry about that disaccharide. Polysaccharides. So we're not into we're into larger numbers. 25, 50, 100 or more, and you get a polysaccharide. So the most common one is starch. So in potatoes and starchy foods, you get a starch, which is usually glucose. Amylose. There's only a couple that I'm going to... Glycogen. You need to know this one. So you eat a lot of food with glucose in it. Your body says, I don't know if you're going to do that again for another 12 to 16 hours, so I'm going to store it in the liver as glycogen. So it builds those glucose molecules up into a polymer, a polysaccharide, glycogen, stores it there, and then you get your blood sugar gets low, and it will start clipping the glucoses back off the glycogen and sending them back out in your bloodstream. So this is an important polysaccharide. It's how you store glucose. All right, and what it might look like, it could be branched like this, glycogen. When you see these numbers, it's talking about the linkage, so like a 1,4 linkage. So you have a carbon, you have a carbon-oxygen here, and where is that going? This is carbon number 4 on the next. So there's your 1,4 linkage. 1 or 4 going down here to 1. That's what that is referring to. So when you see these numbers in the names, a 1,6, you're getting a branch coming off of here, plus the 1,4 linkage in the normal chain. Okay. Cellulose, the most abundant organic material on the face of the earth. Tree trunks, branches, corn stalks, cellulose. All right? So this is the thing that plants, and look how strong a tree trunk is. So what cellulose is, okay, cellulose is highly cross-linked polysaccharide. And so you think of an erector set and you've got stuff going all over the place, it gets pretty strong. And so you can make pretty strong material there. We can't digest that. All right, that's fiber in your diet. And 50 years ago, we thought if you can't digest it, who needs it? And now we think, you need some fiber in your diet. Your digestive system likes some stuff in there. Call it filler, call it whatever you want to call it. But it's kind of nice to have some stuff carrying through your digestive system that you don't necessarily digest. And that's that sort of stuff. I don't know why that slide came up. There's your glycosidic bond, carbon-oxygen carbon bonds. 1,4, the 1,4 link. Okay, finally, oligomers. Remember we said oligomers are 3 or more saccharides? Well, this is what blood type is. What is blood type? The A blood type is these 4 saccharides. So that's not a disaccharide, it's a tetrasaccharide. And it has a galactose. Is that right? Galactose? A celiac, something. 4 different saccharides. That's the antigen A. 4 different saccharides, but 2 of these, so there's 5 there. That's antigen B. That was type O. I'm sorry. O, B, A, and AB. So what is AB? AB. All right? So it's these little saccharides on the outer surface of your hemoglobin or your red blood cells that give blood typing and determine whether someone can donate to and receive, be an acceptor or donor. I think that's 16.